guns are very dangerous. Well, I had a vivid demonstration of the danger of cars last night. I was driving west on Lomas. I was trying to get to Costco to buy some oatmeal, and I was on Lomas going west, and an SUV came up Girard. I had a green light, and this thing went through a red light, slammed into my car. It's actually my wife's car, and hit the back of our car. And our car was spun around almost 360 degrees. The Toyota I was in was going like this, was hit here, and I wound up pointed this way. I had a seatbelt on, fortunately, so my ribs hurt, but I think I'm okay, basically. On the other hand, my favorite dog was in the back seat, didn't have a seatbelt on. Somebody ought to manufacture seatbelts for dogs.
They do.
Huh?
They do. It's like a harness and it clips in.
Really?
Yeah.
If you could send me email, I'd be grateful. Anyway, so I hope he's okay. Anyway, police and fire came, and they were very helpful. Oh, of course, the driver of the SUV, which was relatively new, no insurance, 20-year-old. Presumably she was talking to her friend who was also in the car. Anyway, so cars are very dangerous, and by the way, I've had 2 serious accidents. Both cases, the driver of the guilty car was uninsured. The first accident was in Washington, D.C., a long time ago. Okay, so much for real life. Getting back to physics. Are there any questions? Yes. The what? Yes, I haven't written it yet. And one reason I haven't written it yet is that the course isn't over, so I don't know what I've covered in like this. And the other is I'm thinking of it as a quasi-final exam, and so it's something you can do late in the semester. On the other hand, the other ones, the quizzes on physics and technology for future presidents, those are things you should do. There's so many of them, you ought to do them kind of on time. Otherwise, if they pile up, they're not trivial enough that you can just whip them off. Unless you read the book really carefully and have it really fresh in your head, you might be able to do them all in an afternoon. I don't know. Yes?
In the information, like underneath each of the physics and technology for future presidents exams,
I'm sorry, say it again?
For all of the physics and technology for future presidents, like those quizzes, it says that if you start it after the due date, it won't let you start it.
Damn it, I told them to stop that. So you're saying...
It says that. I don't know if it won't let you, but it says that it won't.
Mine are all, before they were only the ones that were current were showing up, but now all of them are showing up because I've already taken the first 3 at different times.
I took the first one before it was due, and that when I took that one, they were all there. I could see them all, but if you click on the actual exam, before you start it, it says that you can't start it after the due date.
I tell you what, could you send me an email?
Yes.
And my email at khill@unm.edu. Good catch. And explain precisely your problem, and then I'll call up the engineer who works with Learn. I told him that I wanted the students to take be able to take any quiz at any time, any number of times. And he said, okay, he'd do that. And then I called him up a couple of weeks ago, and he said, yeah, he'd get it done. And so I don't know. It's,
I mean, it might just say that. It might just say that you can't, and you still could.
yeah.
But I'm not sure.
Okay. Well, just before you send the email, why don't you make a try and let us send me an email, and then I can then broadcast to the class whatever Eric Girdleman says. In fact, what I could do is put Eric Girdleman's email address on the class website, and you could all have it. And that might get more results than I could get. Okay, we got a number of demos here, and there's the class webpage up there. Let me flick on some of these. Let me click on some of these links. That I just clicked on the link to Stephen Weinberg's article, and what I really recommend that you read is this part 1, which goes on for a page or two. Once you get to part 2, he's then talking about subtle things, and because he's writing in the New York Review rather than the Physical Review, he can't use equations, and so it's, I don't know. I read the article and didn't get a very clear impression of what he was saying. But part 1, I really recommend. Then I mentioned these two. This is a map of dark matter between two clusters of galaxies. Remember, a galaxy is something, is an assemblage of stars that is like 100 billion stars. So this is several galaxies, each with 100 billion stars, and then up here another cluster of galaxies, each with 100 billion stars or so. And yet most of the matter is not in the stars, it's in dark matter, and this is a map of the dark matter, which is most intense here and there and there. Here is a map of dark matter on a vastly larger scale, because these are degrees of declination, and I guess 0 would, I'm not an astronomer, but 0 would be pointing the telescope, I would guess straight in the north, toward the North Star, essentially, I imagine. And then these are sort of degrees of longitude. And so this is an enormous fraction of the sky, and the gray dots, or circles, the gray disks, are clusters of galaxies. Remember, each galaxy is here I should turn these off if I'm. Okay. So each galaxy is 100 billion stars or so, and the red and yellow stuff is dark matter that is estimated by gravitational lensing. And once again, the energy density of the universe is just enough to make the universe flat so that it doesn't recollapse. And so that space is flat, it's not open or closed. And that density, by the way, is equivalent to the density of 5 protons per cubic meter. But since most of the density of the universe is not ordinary matter, but is 2/3 of it is dark energy, which we don't understand, and of the 1/3 that's matter, 80% of that is a kind of matter that we don't know about and have never detected experimentally. And So in fact, only 1 part in 20 of the energy is protons. And so instead of 5 protons per cubic meter, what we have is 1 proton for every 4 cubic meters of empty space. And so space is a far better vacuum than we're able to achieve with, certainly with the vacuum pump that I've used for the demos of in this class, but also better than the vacuum that can be achieved with arbitrarily advanced, well, current vacuum technology, let us say. The vacuum empty space is far better. And as I said, it amounts to, on average, that there's essentially 1 hydrogen atom per 4 cubic meters of space in our universe today. The other things that I invite you to click on is NASA's picture of the day. And this is the first time I've clicked on this particular one, and so this is an inner moon of Saturn. And it's quite remarkable that today we could get images like this. So this is an inner moon of Saturn. By the way, especially when the lights are out, if you have a question, the best thing is to shout. Let me click on a couple of these others. This NASA's picture of the day, of course, changes from day to day. This is a gallery of Hubble images, and so there's just an extraordinary number of them. This one here is an image of Jupiter, and it's even a movie, apparently, of Jupiter, and we can see moons of Jupiter going around Jupiter. And then also, I guess those must be shadows of Jupiter's moons. In other words, when the Jupiter moon gets in between the telescope and Jupiter, what we see is a dark spot. But there are just a million, well, not a million, but many, many, many images here. This, I think, is the dark spot of, well, it's called the red spot, and also a shadow of Ganymede, which is a moon of Jupiter, one of Jupiter's moons. One of the things that's most interesting to look at, I think, is the various spiral galaxies. There's a gorgeous spiral galaxy. And the thought, by the way, is that the dark matter forms a huge sphere, more or less, and that extends roughly this far out from the center of the galaxy. And so you've got all these spiral arms, which are full of stars and dust. And of course, dust is an astronomer's term for gas, actually, and hydrogen, helium, and other metals that were, other elements that were formed in previous stars that had gone supernova and then exploded. So the remnants of supernovas produce all the elements heavier than about beryllium. So this is really a very nice picture of a spiral galaxy. Here is another one, and you can just imagine that's a galaxy of 100 billion stars. One can imagine, well, how many of those stars have planets with life on them? And fact that intelligence evolves very quickly, and the reason is that there's an enormous advantage to intelligence. In fact, one of the smallest creatures is a very tiny worm that only has 1,000 cells. And this worm, in this worm, 300 of its cells are neurons. And of course, those neurons are used partly to control muscles in the worm, but also they supply, the worm uses its neurons to find food and to find mates or whatever it does to reproduce. So intelligence evolves pretty quickly on very small primitive scales, and then eventually you get it evolved to somebody like Einstein or Feinberg, for that matter. And so what do we have? We have maybe a billion planets with some sort of intelligent life, and perhaps 1 million with civilizations as advanced or more advanced than ours. And so it's a very, very big universe, and there's this is a globular cluster, and I think this is a cluster of stars, not a cluster of galaxies. And so I would invite you to click on this link on the web page and then to click on these various images. Many of them are just gorgeous images, and they're also very informative. And they apparently were taken with the Hubble telescope. There's also a whole set of images here that you can get from the Spitzer telescope, and that's at JPL and near Caltech. And they also have somewhere I'm clicking on. Oh, the computer is slow apparently. I guess they set this up years ago on. All right. So here we have various images of galaxies. Well, this one is just in our galaxy, dark clouds on the Milky Way horizon. And there where you have what astronomers call dust, those are regions where there's enough matter for new stars to form. And what happens is these clouds, a cloud of hydrogen collapses, the gravitational energy becomes more and more negative, but because energy is conserved, the kinetic energy of the hydrogen atoms rises, and temperature is a measure of that, and so the gas gets hotter and hotter, and then it collapses further and further, gets hotter and hotter, and more dense, and eventually those reactions that I described on the board on Tuesday can take place, and protons can get converted into neutrons, and then protons and neutrons can combine and form helium, releasing a huge amount of energy, and that's the way the sun creates so much energy. It's basically effectively it's a hydrogen bomb of enormous size, and it's just going on continuously. I'm trying to get back to the web page to show you a couple of others. I didn't find the radio images from NRAO particularly interesting, but if any of you do ham radio operations, you might be interested. let me flip back to this and maybe throw on, go to the slide that has the, so that's the bullet cluster. There's gravitational lensing. And I think I'll just, let's see, how can I make that bigger? There. Okay, well, I'll just leave that up and you can look at it, and I'll do some more demos. Yes, sorry, good question. But by the way, why don't we add a component to this course, public speaking. So when you ask a question, instead of whispering, loud voice so everybody can hear.
So what determines the way that the spiral arms of the galaxy spin?
Good question. True answer, I don't know. As I said, I'm not an astronomer. But what I think is happening is that the galaxy is turning, in other words, all right, this is a guess. As I said, I'm not an astronomer. But I guess that if the pattern looks like this, what that says to me is that this whole thing is turning like that. And the reason for the spin is conservation of angular momentum. What you got originally is an enormous cloud of hydrogen. But the hydrogen is not dense, because as I said, there's one hydrogen atom per 4 cubic meters on average in the universe. And so where the density is as low as the average density of hydrogen, stars don't collapse. But if you go to part of the universe where stars are forming, or for that matter, where a galaxy is forming, what happens when a galaxy forms, as far as I know, is that you have a lot of dark matter. Remember I said that if you have a galaxy, if the bright stars of a galaxy look like, say, a pancake like this, then there's around it a halo or a big sphere of dark matter. And most of the matter there is the dark matter, not the stars. And so what's happened is that a large number of stars moving with, say, random velocities have fallen into this dark matter gravitational field, and they've conserved their angular momentum. So whereas at large distances not much angular momentum was apparent, by the time they got in closer, they were spinning faster and the angular momentum was much more apparent. And somehow that spiral shape took place. On the other hand, it could be totally different. As I said, I'm not an astronomer, and I'm not even sure the astronomers know, because I remember asking astronomers, which is the fundamental galaxy? Is it an elliptical galaxy or a spiral? And you could imagine that if you had two elliptical galaxies collide, they form a spiral galaxy. But I don't think that that's the most popular description of the evolution of spiral galaxies. I will ask my astronomy colleagues and try to remember to get back to you, say something about it on Tuesday. Any other questions? Okay, so I want to do several demos today. Let me do one that's I'm not really looking forward to, because again it's this dizziness business. But, well, the first one isn't going to be making me dizzy. Let's say that I get this thing spun up and I put it here in such a way that angular, the thing is spinning like this, so its angular momentum is pointing out toward you. Well, then the gravitational field of the Earth is going to push it down. But when it pushes it down, what has it done? It's effectively added an extra angular momentum, namely the wheel was there, and now it goes down to, the wheel is pushed in this direction, so there's some momentum that way, and so there's some extra momentum. Well, there's some extra momentum. Maybe the wheel thought I wasn't explaining this properly. But anyway, so when this goes down like that, there is some extra angular momentum this way, and so the wheel has to precess in such a way as to keep the angular momentum straight out at you. So let's see if we can see that. I'm going to turn this thing on. Let's see, I want it to go this way. Okay, this is okay, so there, the angular momentum is pointing, I'm not quite sure which way the wind is spinning, but it's pointing either toward or away from, it's pointing, the main angular momentum is on the axis of the bicycle wheel, but then the gravitational field pushes it down, and so to compensate for that, we've got new angular momentum going this way, which is pointing up. So in other words, the gravitational field, the angular momentum was horizontal originally, the gravitational field made it, pointed it down a little bit, now it's compensated and it's pointing, this precession angular momentum is pointing up, and so the total angular momentum is still horizontal, more or less. All right, I guess I can. What I'm going to do now is show you, again, I'm not sure which way the damn thing is spinning. Well, okay, so it's spinning kind of in a right-handed way. I'm going to change it so that now the angular momentum is pointing either up or down. I think it's pointing up. But now watch what happens when I change it.